Welcome to College Algebra. We're on Unit 4, Expressions, Equations, and Functions. Today we're going to talk about aligning data and using aligned data in modeling that data. What do we mean by aligning data? When finding a model to fit a set of data, it's often easier to use smaller values rather than the given data values. Aligned inputs are simply input values that have been converted to smaller numbers by subtracting the same number from each input. For instance, instead of using t as the actual year, it might be more convenient, change that word to convenient, to use aligned input that is the number of years after 1990. So let's take a look at the application of this. Suppose f of x is equal to 150x squared minus 5x 1,000 candy bars, and that this number of candy bars are produced where x is the number of years past 1990. So what is f of 10? So we're going to take 10, plug it in for x, so 150 times 10 squared minus 5 times 10. And we get that this is 14,950 candy bars. Now in this, what year did we actually calculate the number of candy bars in part A? So we did it in year 10, so 10 years past 1990. So this year is 2000. What must be our value for x in order to calculate the number of candy bars for 2015? So we simply take 2015, subtract 1990, and we get 25 years. So to figure out how many candy bars are produced in 2015, according to this function, we're going to take 25 and plug it in for x. So f of x, or f of 25, is equal to 150 times 25 squared minus 5 times 25, and this is equal to 93,625 candy bars. Public health care expenditures for the period of 1990 to 2012 can be modeled by the function E of t is equal to 738.1 times 1.065 to the power of t, where E of t is in the billions of dollars and t is the number of years past 1990. So what value of t would represent 2010? We simply take 2010. Subtract 1990, and we get that 20 would be the value for t. So approximate the public health care expenditures in 2010. So I'm going to take 20 and plug that in for t. I get 738.1 times 1.065 to the power of 20, and that equals 2,600.80. That would be in the billions. Using this model to estimate the public health care expenditures for 2018. Okay, so 2018 minus 1990 is 28. So E of 28 is equal to 738.1 is 1.065 to the power of 28, and we get that this is 4,304.32. Can we be sure that this is accurate? No, we can't be sure. The only thing that will make this sure data is actually calculating the expenditure. But this is the model we have. And what's nice about using models is we can kind of fill in the data or make predictions based on previous data. Okay, now we're going to use graphical models to interpret given data. This graphing calculator reference sheet gives some directions on how to adjust your window on your calculator. So let's employ some examples of what we mean by this. So in example number 1, we're going to graph on our TI-84 using the given restrictions. So suppose that the cost C of removing P% of the pollution from drinking water is given by this model. C is equal to 5,350 P divided by 100 minus P dollars. Using the restriction on P, we're going to determine the limitation on the horizontal axis of values. So which are the X values that we're going to use on the calculator? All right, first and foremost, what I need to do is I have a plot on from a previous problem. I need to go up to that, hit enter to de-highlight that plot so that it doesn't mess up my current graphing. All right, so I'm going to enter this particular function into my calculator. I get 5,350 P, so we're going to use X for P. All over 100 minus P, or X. So we can tell right away that X is not going to be able to equal 100, and that's because 100 minus 100 is equal to 0. Is equal to 0, and so we can't divide by 0, so 100 is not going to be a possible X value. Another thing that we can just figure out intuitively is P represents a percent. So our P values, because it's a percent, it really can only go from 0 to 100. But we can't include 100, so we're going to say 0 to 100 and close it with parentheses to indicate that 100 will not be included. Nevertheless, we can put 100 in our viewing window. So our X window, we're going to make 0 to 100 by hitting window. We'll make our X min be 0, our X max be 100, and then we will let our Y min be 0 and our Y max be 50,000. How did we get 50,000? Well, our X min, okay, is 0. If I were to plug in 0 in for P or X, I would get 0. So that's why our Y min is 0. The other extreme is 100. Now I can't plug in 100, like we said before, in for P, but I can plug in 99.99 in for P, okay? So if I were to, let's go to the graph, hit second calc value and 99.99, okay? I would get 5,500. I would get really close to, let's see, what is this? 1, 2, I would get 53 million, okay? But if I were to come down a little bit, trace it, I just want to make sure that I can get most of the graph. There's no way I'm going to be able to remove 100% of the pollution. Okay, so if I got 90 to 90. Now I could extend the graph so that I could see more of it and get to 50 million. But I would say probably here, okay, so the end of the graph is 48,973. So 50,000 is probably a good window for Y so that I can see most of the graph. All right, so this is a really big number. We came down a little bit so that we would be able to see the whole graph. Now, why is it reasonable to graph the model on a window with the limitation of C being greater than or equal to 0? Well, what is C? C is cost, right? When does it ever happen that cost is negative? Not so much ever. So our cost will not be negative. So we can rest assured that limiting the cost of C being greater than or equal to 0 is reasonable. All right, now we want to find the point on the graph that corresponds to P is equal to 90. In other words, what is the cost of removing 90% of the pollution? So I did second calc value 90, and we get $48,150 to remove that pollution. The second problem says, how can we, it's kind of giving us an idea of learning how to determine what our viewing window is going to be. So this one's about aging workers, the millions of Americans who are working full-time jobs at selected ages from 20 to 65 can be modeled as a function of their age X. This model, negative 0.000362 x cubed plus 0.0401 x squared minus 1.39 x plus 21.7 is the model that represents the millions of workers in the country. 362 x cubed plus 0.0401 x squared minus 1.39x plus 21.7. Okay, so the question is, what would be an appropriate viewing window for these x values? We can see by hitting zoom 0 that this is an interesting looking graph, okay? It's a cubic graph, so it has this particular shape, but we want to limit our viewing window for what would be reasonable piece of this model. Okay, so what would be our X? Well, what is X? X is the ages of our population. So 20 to 65. That would be an appropriate viewing window. Okay? An appropriate viewing window for the Y values would be the corresponding Y values to these two X values. So in other words, what is F of 20 and F of 65? All right, so I'm going to hit second calc value 20. F of 20 is 7.044. Okay, second calc value 65 is 1.358. Okay, so that I can include both of these numbers, I'm going to let my Y window restriction go from 1 to 8. All right, let's adjust our window. Hit window. We want our X min to be 20, our X max to be 65, our Y min to be 1, and our Y max to be 8. All right, now let's look at the model. This is the portion of the graph that we need for our particular purposes. So it says, use the model now to estimate the number of Americans age 55 and age 64 who are working full-time. So we need f of 55, second calc value 55. So this is about 6.3, what are we in, million? Yes, million. And then f of 64, second calc value, 64, 2.09 million. All right, so that's how we can adjust our window to figure out what restrictions we need on our domain and range for the use of our particular purposes in using the model. Again, you have to look at what's reasonable for your domain. So here our ages were already restricted from 20 to 65, and then we took these x values and plugged them into the function in order to figure out what would be our minimum and our maximum for our window in the y, for the y's or the range.